The universe appears silent, a vast and endless ocean of darkness, yet hidden within this silence, something moves, not in sound or in fire, but in the invisible language of forces. A storm is ridden into the very emptiness between galaxies. It does not rage with winds. It does not blaze with lightning. Instead, it is frozen, still balanced, and unrelenting. Galaxies spin like leaves caught in a current. Black holes bend the path of light, pulling at the seams of reality. Dark energy stretches space-time itself, an unseen tide that accelerates the expansion of the cosmos. All of it whispers of the same secret. The void is not empty. What appears to be nothing is alive with hidden tension, a storm locked in silence. But storms are meant to rise and fall, to roar and then to fade. What if this one does not? What if the frozen storm at the heart of space is not a passing phase, but the very foundation of existence? If it is eternal, does it cradle the universe, holding every atom, every star, every galaxy in its grip? Or is it a shadow, the trace of something even deeper, waiting to break? The frozen storm may be the vacuum itself, quantum fields restless, even in stillness. The energy of nothing, dark matter and dark energy that guide the fate of the cosmos. It is a storm without sound, a storm with no end, and perhaps, one day, a storm that will decide the future of reality itself. Long before telescopes, long before equations could be written to capture the rhythm of the stars, human beings looked upward and wondered. To the ancients, the heavens appeared immutable, a dome of perfection untouched by the chaos of earthly storms. The night sky seemed eternal, unchanging, an infinite stage upon which the fires of the gods were placed. For Aristotle, the void was impossible. He rejected the notion of nothing, believing that nature abhorred the vacuum. To him, space was always filled with something, be it air, ether, or the substance of the celestial spheres. A true emptiness, a place devoid of substance, was inconceivable. The void was not only an absence, it was a philosophical threat. Centuries later, other voices arose. The atomists of ancient Greece, Leucippus and Democritus, dared to imagine a universe built of indivisible atoms moving in an infinite void. Their vision of nothingness was radical. Space could exist without substance, and the dance of atoms within it would create the world of matter. Yet their insights, too far ahead of their time, were buried under centuries of Aristotelian dominance. It would take the scientific revolution to resurrect the void as something more than philosophy. With Isaac Newton came a new vision, absolute. Space, a stage upon which matter could move and forces could act. In Newton's conception, the vacuum was an empty arena, vast and still, indifferent to the motions of planets and stars. The void itself was not alive, but the silent framework of existence. To him, space was a container, infinite and unchanging, upon which gravity inscribed its influence. But Newton's emptiness was not to last. In the early 20th century, Albert Einstein shattered the stage with his general theory of relativity. Space and time became dynamic, inseparable from matter and energy. The void was no longer passive. It bent, curved, and rippled in response to the presence of mass. A star could shape the geometry around it, and light itself would follow the curves of space-time. The emptiness between objects was revealed to be part of the drama itself. What seemed like nothing became something with weight and consequence. Then, as physics turned inward, the storm revealed itself in miniature. At the dawn of the quantum age, Max Planck introduced the radical notion that energy comes in discrete packets, quanta. What had once seemed continuous and smooth was revealed to be granular, restless, vibrating with hidden structure. Niels Bohr's atoms suggested electrons did not orbit smoothly, but leaped between discrete states. Louis de Broglie imagined particles not only as masses, but as waves, undulating with probabilities. And then Erwin Schrödinger offered his equation, a mathematical symphony in which every particle became a wave function, spread across possibilities. Never still, the void, it turned out, was never empty. Werner Heisenberg's uncertainty principle declared that at the smallest scales there could be no perfect silence. Position and momentum, energy and time, all were bound by fundamental uncertainty. Even in vacuum, fluctuations were unavoidable. Nothingness became a seething ocean of potential, restless and inescapable in 1930. Paul Dirac expanded the picture with his sea of negative energy. To explain the mathematics of quantum theory, he suggested that the vacuum was filled with invisible particles, an infinite ocean beneath the surface of reality. Holes in this sea gave rise to new phenomena: antimatter, particles identical to electrons, but with opposite charge. Out of the void, entire families of matter emerged. Then came proof, not only in theory, but in experiment. In 1948, Dutch physicist Hendrik Casimir proposed an audacious idea. If two metal plates were placed extremely close together, the quantum fluctuations of the vacuum outside them would press inward, while the waves inside would be restricted. The plates would feel a force, not from any visible source, but from the energy of empty space itself. Experiments confirmed it. The Casimir effect became a direct window into the storm hidden inside nothingness. The void was not silent. It pulled, it pressed. It moved. By the mid-20th century, cosmology joined the quantum picture. The universe was not static, but expanding. Edwin Hubble had shown in the 1920s that galaxies recede from one another, the fabric of space stretching, like the surface of an inflating balloon. In Einstein's equations, this expansion demanded an engine, a term he had once inserted and then abandoned. The cosmological constant for Einstein. The constant was a mistake, a blunder to preserve a static cosmos that never existed. But decades later, it would be reborn. The frozen storm at the heart of space was revealed not only in laboratories, not only in the equations of quantum mechanics, but in the very structure of the cosmos. The expansion of the universe itself was tied to the nature of the vacuum by the late 20th century. A startling idea emerged. The vacuum was not neutral. It was an active force. Its fluctuations were not only measurable on small scales, but perhaps responsible for the greatest motions of the universe itself. The storm had been hiding in plain sight. What philosophers had called nothing was instead the most fertile field in existence. Within it, particles flickered into being and dissolved again, giving rise to forces, masses, and perhaps even the birth of the universe itself. The discovery that the void is alive changed everything. Stars, galaxies, black holes, all of them may be temporary, fleeting patterns dancing upon an eternal backdrop. But the backdrop itself, the frozen storm of the vacuum, is the one element that never rests. It is a paradox, a storm that never rages, yet never ends, a sea that appears still, yet is filled with invisible waves. From Aristotle's rejection of the void to Einstein's curved space-time, from Planck's quanta to the Casimir effect, the mystery has deepened. The frozen storm is real. The vacuum is not absence, but presence. Not silence, but a whisper too soft for ordinary senses to hear. And yet, with each discovery, the unease grows. Because if the void is alive, then what sustains its balance? And if it is a storm, could it ever break? For centuries, the void had been imagined as passive, a stage for the play of matter, a background to the drama of galaxies and stars. But the 20th century forced a revelation more profound and more disturbing. The void itself was not empty. It was alive. Quantum theory unveiled the first hint of this revelation. At the heart of the mathematics was a peculiar fact. Even in its lowest energy state, a system could never be perfectly still. Every atom, every field, every corner of existence retained a residue of energy, the so-called zero-point energy. This was not an optional feature of physics, not an imperfection in calculation. It was a necessity written into the uncertainty principle itself. If particles and fields could ever truly stop fluctuating, then their positions and momenta could be known with infinite precision, and quantum mechanics would collapse. Thus, the vacuum was doomed to seethe. Even stripped of all matter, space could not escape its own restlessness. The Casimir effect provided direct evidence. Two metal plates, placed nanometers apart, experienced an attraction that could not be explained by any classical force. It came from the suppression of certain quantum fluctuations between them. The plates, in a sense, were being pushed together by the pressure of the void itself. The Lamb shift, a subtle alteration in the energy levels of hydrogen atoms, offered another proof, as did vacuum polarization, where virtual particles briefly distort electric fields. The shock was not that the void had effects, but that its influence was everywhere. Every interaction, every particle, every field was bound to the frozen storm. And then came the discovery that turned the quiet hum of quantum vacuum into a cosmic scream in 1998. Two independent teams observing distant Type Ia supernova noticed something strange. The light curves of these dying stars, used as standard candles to measure cosmic distances, did not fit the expected pattern. Galaxies were not merely receding as Hubble had shown. Their recession was accelerating. The expansion of the universe was speeding up. This revelation shattered assumptions. Gravity, the great attractor, should have slowed the expansion over billions of years. Instead, something unseen was pushing galaxies apart. The simplest explanation was an energy inherent in the vacuum itself, a cosmological constant reborn under the name dark energy. Here, the frozen storm revealed its terrifying power. It did not merely flicker in hidden corners or tug on metal plates in laboratories. It commanded the fate of the cosmos. Roughly 70% of the universe, cosmologists concluded, was made of this dark energy. The void was not a passive backdrop. It was the main character. But with this recognition came the greatest theoretical mismatch in the history of science. Quantum field theory attempted to calculate the energy of the vacuum by summing the fluctuations of all possible fields. The result was staggering, 10 times larger than the observed value. The difference was not a mere error, not a tweakable parameter. It was the greatest chasm between theory and observation ever encountered, the cosmological constant problem to physicists. This was more than a puzzle. It was a wound in the foundation of knowledge. If the storm was truly this powerful, the universe should have torn itself apart long ago. Yet if it were weaker, galaxies would never have formed. Somehow, it was tuned to a value infinitesimally small compared to theory, yet not zero. just enough to dominate cosmic history billions of years after the Big Bang. This tuning felt unnatural, even ominous. Was it coincidence? Was it design? Or was there a deeper law, still hidden, that balanced the storm with exquisite precision? The philosophical implications were terrifying. The void, long imagined as nothingness, was revealed as the most potent force in existence. Its balance was fragile, precarious. If altered, even slightly, reality itself could disintegrate. This fear took a darker form in the idea of vacuum metastability. Perhaps our universe was not in the true ground state of the vacuum at all. Perhaps it was balanced on a plateau, a false vacuum. If so, a quantum tunneling event could one day hurl it into a deeper, lower energy state. In that instant, the constants of nature would change, atoms would disintegrate, and the laws of physics would be rewritten. The bubble of destruction would expand at nearly the speed of light, unstoppable, erasing everything in its path. The void, in this vision, was not eternal stability, but a frozen storm waiting to break. Even without such apocalyptic visions, the shock persisted. Physicists had always assumed that the laws of nature could be measured, tested, and preserved. But if the foundation of those laws, the very structure of space itself, was governed by an invisible, uncontrollable storm, then certainty itself was lost. This realization blurred the line between physics and philosophy. If the void was active, could it be thought of as substance? If the vacuum was the stage, then it was also the actor, shaping every event, yet immune to direct observation. The human mind recoiled at the paradox. Nothingness was not nothing, but everything. The emotional weight of this discovery is difficult to overstate. For millennia, stars had symbolized permanence, guiding navigation and calendars. But now, even permanence dissolved. Not only would stars die, not only would galaxies fade, but the emptiness between them was revealed to be alive with storm. Reality itself was provisional, its balance hanging on forces that no human hand could touch. Too many, the most unsettling aspect was scale. On the smallest levels, the storm manifested as virtual particles flickering in and out of being. On the larger scales, it dictated the acceleration of billions of galaxies. From quantum fluctuations to cosmic expansion, it ruled every boundary of existence, and yet its true nature remained invisible. Dark energy could not be bottled or touched. Zero-point energy could not be switched off. No telescope could show the storm directly. It could only be inferred through its fingerprints, glimpsed in the behavior of particles, stars, and galaxies. The shock was not merely intellectual, it was existential. The void had turned from an emptiness to a presence, from a silence to a storm. The laws of physics were no longer secure. Beneath them lay an abyss, and no one could say whether it was stable. The frozen storm was not a metaphor. It was reality itself. Once the first shock had passed, the realization that the vacuum was neither empty nor benign, science turned to the slow, meticulous task of probing its depths. If the storm was real, its traces had to be written across the cosmos. The first great cartographers of this frozen tempest were satellites that mapped the afterglow of the Big Bang. The Cosmic Background Explorer COBE, launched in 1989, captured the faint microwave radiation that had streamed freely since the universe was 380,000 years old. COBE revealed that the cosmos was not perfectly smooth, but laced with fluctuations, tiny differences in temperature, 1 part in 100,000. These were the seeds of galaxies. but they were also signatures of the vacuum of quantum fluctuations, stretched across the newborn universe by inflation. A decade later, the Wilkinson Microwave Anisotropy Probe, WMAP, sharpened the view. The frozen storm's fingerprints became clearer, patterns of acoustic peaks, relics of pressure waves, rippling through the primordial plasma. These were fossilized in the cosmic microwave background, frozen when matter and radiation parted ways. And behind those ripples was the vacuum itself, whose fluctuations had supplied the randomness that became structure. The Planck satellite, launched by the European Space Agency in 2009, went further still. It mapped the sky with exquisite precision, confirming that the universe is astonishingly flat and uniform, far smoother than chance would suggest. Once again, the storm was implicated. Without a primordial fluctuation spectrum generated by the quantum vacuum, the cosmic web would not exist. But these were only the broad brushstrokes. The deeper the gaze, the stranger the details became. Physicists turned to baryon-acoustic oscillations, subtle imprints left in the distribution of galaxies. These frozen sound waves had traveled through the early universe, halting when matter decoupled from radiation. Their echo remains today in the large-scale clustering of galaxies, like a fossilized heartbeat of the frozen storm. By measuring them, scientists could trace the expansion history of the cosmos, and again they found the invisible hand of dark energy driving acceleration at smaller scales. The storm revealed itself through vacuum polarization. Virtual particles, electron-positron pairs, quarks and antiquarks flickered in and out of existence, briefly altering the behavior of fields. These ephemeral ghosts could never be directly seen, but their presence shifted results: the Lamb shift in hydrogen, the anomalous magnetic moment of the electron, the behavior of photons in strong fields. Each was a whisper of the storm. The Higgs field added another layer of revelation. In 2012, the Large Hadron Collider LHC confirmed the Higgs boson, a particle linked to an invisible field that permeates all space. This field gives mass to particles, anchoring them in reality. Without it, electrons would be massless, atoms would not form, chemistry would be impossible. The Higgs field was not separate from the storm. It was one of its faces. The frozen storm was not confined to fluctuations of nothingness. It was the invisible lattice on which matter itself was built. At the edges of black holes, the storm became even more dramatic. Stephen Hawking's work in the 1970s showed that near an event horizon, vacuum fluctuations could tear apart virtual particle pairs, allowing one to escape while the other fell inward. The result was Hawking radiation. Black holes, long thought to be eternal, would slowly evaporate. This revelation tied together gravity, quantum fields, and thermodynamics, three of nature's pillars, in a way that defied simplicity. The vacuum was not merely a passive stage for black holes. It was their undoing. Experiments and calculations within quantum field theory, QFT, pushed the storm further into paradox. Every known particle, from photons to gluons, carried a field. Each field contributed to the vacuum's energy. But their sum, vast beyond comprehension, should have warped space-time violently. Yet the actual cosmos was tranquil enough for galaxies and life to exist. The storm raged invisibly, but the universe balanced on a knife's edge. Deeper still lay the cosmological puzzles, the horizon problem. Why distant regions of the universe, too far apart to ever have exchanged signals, are nearly identical? In temperature, the flatness problem, why the geometry of the universe is so finely tuned to be flat, rather than wildly curved. Both problems pointed back to the storm. Inflation theory, a burst of exponential expansion in the first trillionth of a second, could explain them by stretching quantum fluctuations to cosmic scales. But inflation itself required a vacuum state of extraordinary energy, then an abrupt decay to the calmer storm we see today. The vacuum was not simply present. It was an active player in the universe's birth. As investigations deepened, the storm began to feel less like a background and more like a hidden order. Every experiment seemed to uncover another layer of its influence. Every anomaly hinted at a truth beneath physics as we knew it. And yet, the more that was learned, the less secure the foundations became. If the storm was real, was it stable? Could its balance shift? The Higgs boson's measured mass suggested that our vacuum might be metastable, perched between stability and collapse. If so, then the frozen storm was not eternal. It was a plateau, destined one day to give way to a lower energy state. And when it did, reality itself would be rewritten. The deeper investigation did not soothe the shock. It sharpened it. The storm was not only measurable in laboratories and observable in the heavens. It was necessary for the very existence of matter, galaxies, and life. Without it, there would be nothing. Yet with it came the constant possibility of collapse. The frozen storm at the heart of space was no longer theory, no longer philosophy. It was fact, tested in atom, star, and cosmos alike. It was the stage, the script, and the director. And if it faltered, the play itself would end. The more the storm was measured, the more its paradoxes grew. What had begun as a whisper of virtual particles and subtle shifts in experiments expanded into a cosmic force shaping the fate of everything. The frozen storm was not merely a curiosity. At the heart of space, it was the architect of the universe's destiny. In 1998, astronomers measuring distant type Ia supernova revealed something astonishing. The expansion of the universe was not slowing under the pull of gravity. It was accelerating. Galaxies were not only receding, they were fleeing ever faster, as if pushed apart by an invisible wind. The frozen storm had a name now: dark energy, a form of energy that pervades the vacuum, woven into space-time itself. But, unlike any familiar storm, this one did not rage louder with time. It remained eerily steady. Its energy density appeared constant even as the universe expanded, so that more and more of it came into existence with every passing second. The cosmos was filling with nothingness, and yet that nothingness had power. The consequences were profound. As expansion accelerated, more galaxies slipped beyond our cosmic horizon, the boundary of what could ever be observed. One by one, ancient islands of light vanished into darkness, their messages forever severed from us. The frozen storm was not only reshaping the future, it was erasing the past. And still, the questions deepened. Was this storm eternal, or was it balanced? On the edge of catastrophe, physicists considered the possibility of false vacuum decay. If the vacuum we inhabit is only a metastable state, then somewhere in its depths may lie a lower energy configuration. A single quantum fluctuation could trigger a bubble of true vacuum, expanding outward at nearly the speed of light. Within its frontier, the laws of physics themselves would be rewritten. Electrons might no longer bind to nuclei. Atoms might dissolve. Space-time itself could fracture. The frozen storm would not rage, but collapse, and reality would end without warning. This possibility was not fantasy. The measured mass of the Higgs boson suggested precisely such a precarious balance. The numbers implied that our universe rests uneasily between stability and decay. The storm, frozen though it seemed, might in truth be temporary. Even without collapse, its long-term consequences are chilling. In the far future, as acceleration continues, distant galaxies will race so quickly beyond the horizon that their light will never reach us. Stars will burn out. Black holes will evaporate. 1 trillion years from now, only the local group of galaxies may remain, floating in an ocean of darkness. The frozen storm will rule, stretching space-time so completely that contact with the wider universe will be forever lost. For those who imagine eternity as endless time, this vision offers only silence. The storm ensures not endless richness, but eternal isolation. Yet even this is not the deepest escalation, for the storm touches not just matter and motion, but information itself. In black hole physics, horizons conceal what falls within, does information disappear, violating the principles of quantum mechanics? Or is it somehow encoded on the horizon's surface? This puzzle led to the holographic principle, the radical idea that the three-dimensional universe may be described by information, written on a two-dimensional boundary. If true for black holes, might it also be true for the cosmos as a whole? The cosmic horizon, defined by the storm's acceleration, may not simply be a boundary of sight but a screen on which reality itself is inscribed. In this view, the frozen storm does not merely erase, it also encodes. Every fluctuation, every photon, every act of existence may be preserved in the storm's silent weave. But if the storm encodes, what language does it use? And if it collapses, what happens to the information it holds? The storm was no longer merely a property of space. It was becoming the foundation of space-time itself. Quantum entanglement, the ghostly link between particles across distance, began to show ties to geometry. The conjecture equals EPR, proposed by Juan Maldacena and Leonard Susskind, suggested that entangled particles might be connected by microscopic wormholes. If so, then the fabric of space-time could emerge from entanglement itself, from the same quantum waves that form the frozen storm. This deepened the paradox. If the storm underpins space-time, then its collapse would unravel not just matter, but the stage on which reality unfolds. The storm was not the weather within the universe. It was the universe. The implications stretch to philosophy. What does it mean to live in a cosmos where emptiness is not void but energy, where silence conceals the greatest dynamo of all? If storms rage, they eventually subside. But what if the frozen storm is permanent? Does eternity mean unending creation or unending destruction? For some theorists, the storm may never cease. Its balance may define a true vacuum, eternal and immutable. In that case, galaxies will continue to vanish, entropy will grow, and the universe will end not in fire, but in an infinite whisper, a heat death where even quantum fluctuations fade. For others, the storm may itself be an artifact of something deeper. String theory imagines it as vibrations of hidden dimensions. Loop quantum gravity suggests it emerges from discrete geometry, tiny grains of space-time that shimmer with probability. In these visions, the frozen storm is a mask, the visible surface of a truth we cannot yet perceive. What escalated the mystery most of all was this: humanity, perched on a small planet, was uncovering forces that determined not only the fate of stars and galaxies, but the very possibility of existence. And at the heart of it all was a paradoxical storm, frozen yet decisive, silent yet omnipotent. The escalation had transformed awe into unease. The storm was not a passive stage, but an active player. It dictated the expansion of the cosmos. It concealed and perhaps destroyed information. It threatened collapse into a lower state. And it raised a haunting possibility that what we call reality is nothing more than a temporary balance within a storm too vast to control. In this deepening, the question no longer was whether the storm existed. The question was how much longer it could last. The first blow to human intuition came with the revelation that the vacuum was not what it seemed. For centuries, emptiness had been considered absence, a void stripped of all form and substance. Yet 20th century physics began to erode this simple certainty. At the quantum level, nothingness revealed itself as turbulent. Werner Heisenberg's uncertainty principle ensured that no field, no particle, no fragment of reality could ever be perfectly still. Even the vacuum, once assumed to be an ocean of silence, seethed with fluctuations, a restless dance of energy, particles appearing and vanishing in ephemeral flashes. The Casimir effect became the first striking evidence. In 1948, Dutch physicist Hendrik Casimir predicted that two uncharged metal plates placed close together in a vacuum would experience a subtle force, as if the emptiness between them was pushing them together. Decades later, this effect was confirmed, proving that the vacuum was not void, but alive. The plates moved because quantum fields outside them surged more strongly than those within. The storm, at the heart of space, once invisible, left its fingerprint on metal. Other surprises followed. The Lamb shift, measured in hydrogen atoms, revealed that even the simplest element could not escape the storm. Tiny shifts in electron energy levels proved that quantum fluctuations were constantly jostling reality. This was not theory, it was experiment. The void was an active agent, reshaping atoms themselves. But the deepest shock would come not from atomic physics, but from the cosmos itself. In 1998, two teams studying distant supernova expected to find evidence that cosmic expansion was slowing under the pull of gravity. Instead, they found acceleration. The galaxies were not merely drifting apart, they were fleeing faster and faster, propelled by something invisible embedded in the vacuum. This discovery gave a name to the storm: dark energy. Its presence was not confined to laboratories or equations. It was steering the fate of the entire universe. 70% of the cosmos was not matter, not radiation, not anything tangible, but the frozen storm itself, yet its scale defied comprehension. Quantum field theory predicted that the vacuum's zero-point energy should be staggeringly immense, to 120 orders of magnitude greater than observed. The worst mismatch in physics, a calculation that screamed paradox. If the storm was as violent as mathematics implied, space-time would have torn itself apart instantly after the Big Bang. Instead, the balance was subtle, delicate, inexplicable. This was the cosmological constant problem, the greatest embarrassment of modern physics. Why was the storm so finely tuned, so quiet, when theory demanded violence? Was there an unknown symmetry suppressing its fury, or were we living in a universe precariously balanced, poised on the edge of collapse? The terror lay not only in what was known, but in what was implied. If the frozen storm ever shifted, if its balance were disturbed, the entire universe could unravel. A false vacuum collapse, predicted in speculative models, could erase all familiar physics in an expanding bubble of annihilation. The storm would not merely power expansion, it would rewrite existence. Philosophers found new dread here. Emptiness was no longer passive. The void itself was dynamic, unstable, and filled with potential catastrophe. Reality was no longer built upon a solid foundation, but on the surface of an invisible sea whose depth no one could measure. In this vision, the cosmos was not a cathedral, resting upon eternal stone, but a ship adrift upon a frozen storm, its silence hiding turbulence that could at any instant break. The revelation that the vacuum was alive, a storm without wind, a sea without waves, demanded deeper scrutiny. If emptiness itself shaped the universe, then every telescope, every satellite, every detector became a probe into the storm's invisible structure. The void was no longer the background of physics. It was the subject. The first great cartographers of this hidden ocean were the satellites that mapped the relic glow of the Big Bang. In the early 1990s, the cosmic background explorer COBE sent back a vision of the universe as it was, nearly 14 billion years ago. To the human eye, it looked like static, a faint wash of microwaves stretched thin by time. Yet hidden in that noise were the earliest ripples of the frozen storm. Tiny fluctuations in temperature, no more than 1 part in 100,000, betrayed the influence of vacuum energy in the infant cosmos. These faint imprints were the seeds from which galaxies, stars, and planets would grow. A decade later, the Wilkinson Microwave Anisotropy Probe, WMAP, sharpened this view, and the European Space Agency's Planck satellite refined it further. Still, their exquisite maps of the cosmic microwave background revealed not only the size and age of the universe, but also its geometry, astonishingly flat, as though stretched upon an invisible scaffolding. Here was the storm again, exerting pressure on the very shape of space. The balance was so delicate, so precise, that physicists were forced to ask whether it was coincidence or evidence of some deeper hidden principle beyond the background glow. Galaxies themselves carried whispers of the storm as they formed and clustered under gravity. Their arrangement froze into patterns known as baryon acoustic oscillations, faint relic sound waves from the early universe. These frozen ripples, detectable today in the large-scale distribution of galaxies, bear the unmistakable trace of the vacuum's invisible hand. The storm was not silent after all. It had sung in the early cosmos, and the echo was still imprinted. In the stars, on smaller scales, the vacuum's fingerprints were equally profound. In laboratories, quantum electrodynamics described how the void polarized itself, spawning virtual pairs of particles and antiparticles that flickered into existence before annihilating. These ephemeral storms subtly altered the forces between charged particles, effects measurable in atomic experiments with breathtaking precision. The Casimir effect had been the first clear sign, but countless others followed, each proving that the vacuum was not nothing, but a restless stage where quantum fields collided in silence. Particle physics revealed another facet of the frozen storm in the Higgs field. Proposed in the 1960s and confirmed in 2012 at CERN's Large Hadron Collider, the Higgs field is an omnipresent background that grants mass to elementary particles. Without it, electrons would flit massless through space, atoms could not bind, and stars could not ignite. It was yet another reminder that the storm was not passive. It structured reality itself. Even black holes, the most extreme objects in the universe, unveiled the power of the void. Stephen Hawking's calculations in the 1970s revealed that quantum fluctuations near an event horizon should generate radiation. slowly evaporating the black hole itself. This startling idea meant that the vacuum was not only active in flat space, but also decisive in the most curved and violent spacetimes. Black holes, once thought to be silent prisons of matter, would in time dissolve, their existence mediated by the frozen storm. Quantum field theory extended this picture further still. Every type of particle, from photons to neutrinos to quarks, contributed its own field to the vacuum. Each field hummed with zero-point energy, each adding to the storm's intensity. Yet the combined sum, when calculated, yielded absurd results. Energies so large they would crush space-time. To reconcile theory with observation required a cancellation, a fine-tuning beyond reason. Why the universe allowed such delicate balance remained a mystery. As the data grew, anomalies deepened. The horizon problem, why distant regions of the universe share the same temperature, despite being causally disconnected, suggested that the storm had once unleashed a burst of inflation, an expansion faster than light, smoothing and flattening space before time itself could measure its own flow. The flatness problem, equally unsettling, implied that the storm had tuned the density of the universe to a knife's edge. A fraction more, and the cosmos would have collapsed. A fraction less, and it would have flown apart too rapidly for stars to form. These puzzles pointed toward a storm that was not chaotic, but exquisitely balanced. Why should the void be so finely tuned? Was this balance the result of chance? An accident in a multiverse of infinite possibilities? Or did the frozen storm conceal laws deeper than any human had yet imagined? By the early 21st century, one thing was certain. The frozen storm was not a metaphor, but a measurable, calculable, observable reality. It was written into the microwave background, into the clustering of galaxies, into the flicker of atomic energy levels, into the evaporation of black holes. It was everywhere, yet hidden from sight. And the more scientists studied it, the more precarious reality seemed. For the void was not emptiness. It was a storm that could be mapped, measured, and felt, but never stilled. And behind its frozen stillness, a deeper unease lingered. If the storm was so finely tuned, could it also be temporary? Could its balance one day break? The more the universe revealed, the stranger the frozen storm appeared to be. What once seemed like a silent background to existence was now revealed as the most powerful force of all, dark energy. The quiet engine of acceleration, the galaxies, once imagined as eternal beacons, are slipping away. Every second, the storm stretches the fabric of space, not in sudden tempests, but in a steady, accelerating drift, so relentless that light itself cannot keep pace. Already, galaxies at the farthest horizons have crossed beyond the cosmic boundary. Their light, however bright, will never reach us. The storm has erased them from our sky, as if they had never existed at all. In this accelerating universe, the storm is not neutral, it is selective. It divides the cosmos into two fates: what remains, bound together by gravity, and what is carried away forever into silence. The local group of galaxies, the Milky Way, Andromeda, and their satellites, is held by mutual gravity, destined to merge into one colossal structure. But beyond this island, everything else drifts away, vanishing into eternal exile. In 1 trillion years, no telescope, no matter how powerful, will see beyond this single cluster of stars. The storm will have erased the history of the cosmos, leaving future observers in ignorance of the universe's grand story. Yet even this isolation is not the deepest fear. For physicists, the storm raises an even darker possibility. instability. What if the frozen balance we see is only temporary? Quantum field theory suggests that the vacuum we inhabit may not be the lowest possible state of energy. Instead, it could be a false vacuum, a precarious plateau in the landscape of quantum fields. If this is true, then beneath the calm of the frozen storm lies a deeper abyss. And if the vacuum were to tunnel into that abyss, it would unleash a bubble of destruction, expanding at near the speed of light, rewriting the very constants of physics as it spread. Within this bubble, atoms could not hold together. The forces that govern matter would be reset to alien values. Chemistry would dissolve, stars would extinguish, space-time itself would be remade in an instant. To those who lived in its path, there would be no warning. One moment, a world. The next, silence. This is the existential terror of vacuum metastability. The idea that the frozen storm is not eternal, but only waiting. Other mysteries deepen the unease. At the very edge of physics, researchers are uncovering hints that the storm is not merely energy, but also information. Quantum entanglement, that strange link between particles across space, seems woven into the very fabric of the void. In recent years, theorists have suggested that space-time itself may emerge from entanglement, that the geometry of the universe is not fundamental, but constructed from quantum connections spread across the storm. If so, then the frozen storm is not simply the background of existence, but its foundation. Without it, there is no fabric, no geometry, no dimension in which stars could shine or life could unfold. The void is not absence, but structure. A structure so delicate that we do not yet know if it is permanent. The holographic principle adds another dimension to the paradox. According to this radical idea, everything inside the universe, every particle, every galaxy, every memory could be encoded on its horizons. Just as the surface of a black hole holds the information of all that falls within, so too might the cosmic horizon contain the sum of reality. If this is true, then the storm is not only frozen, but also archival. It holds the past, the present, and perhaps the future, not in stars or matter, but in the shimmering uncertainty of quantum information. But here lies the most haunting question. If the storm is the bedrock of reality, what happens if it breaks? In one vision, the storm persists, stretching the universe into an eternal frozen silence, a cosmos that accelerates forever, where galaxies vanish, stars extinguish, and black holes evaporate, until all that remains is a thin whisper of radiation stretched to invisibility. The storm becomes the ruler of an eternal night. In another vision, the false vacuum collapses, rewriting the rules of existence. In this case, the storm is not eternal but catastrophic, ending not with silence, but with transformation, and in yet another vision, the storm may not be alone. If inflation theory is correct, the universe itself was born in a storm of vacuum energy, a burst of expansion so violent it smoothed and flattened the cosmos, leaving behind the seeds of galaxies. Some versions of inflation never end. Instead, they give rise to eternal inflation, where bubbles of space-time are born endlessly in an infinite froth. In this view, the frozen storm we see is not unique, but one of countless storms across a multiverse, each with different balances, different laws, different destinies. In every possibility, the storm is central. It decides what galaxies exist, what particles are stable, what forces bind, what futures unfold. And so the escalation of the mystery becomes unavoidable. The frozen storm is not passive emptiness. It is the architect of the universe. If it endures, we endure. If it shifts, all dissolves. If it is but one instance among many, then our entire cosmos is a local illusion. A single note in an infinite symphony. At the heart of space, the storm remains silent, but its silence is deceptive. It is frozen, yes, yet it is also alive. The storm's stillness carries weight. It is not the silence of peace, but the silence of tension, a silence that could last forever or break in an instant. The frozen storm is the question upon which physics, cosmology, and philosophy converge. It is the invisible force that defines the fate of the stars and the boundaries of imagination. And as galaxies continue to vanish, carried into unreachable horizons, the storm seems less like a distant abstraction and more like a pulse, faint but relentless, a heartbeat at the center of existence. A storm that has no sound, yet governs all things. If the frozen storm is real, if the void itself is alive with tension, then the next question is unavoidable. What is it? Theories bloom like constellations, each attempting to explain the storm that binds the universe. None are complete. Each offers a vision, partial, tantalizing, but shadowed by doubt. The first and most ancient candidate is the cosmological constant. In 1917, Albert Einstein inserted this term into his equations of general relativity, a tiny counterforce to gravity. Without it, the universe, under the pull of its own mass, should collapse. With it, the cosmos could remain static. He later abandoned the constant, calling it his greatest blunder. After Hubble revealed that galaxies are expanding outward. Yet decades later, the discovery of accelerating expansion resurrected it. Perhaps Einstein was not wrong, but premature. The cosmological constant may be the simplest explanation of the storm, a property of space-time itself, a constant energy, woven into the vacuum. But simplicity hides terror. If the constant is truly constant, then the storm will never subside. It will stretch space eternally, pulling galaxies apart, carrying the universe into an endless future of isolation and silence. An infinite expansion with no end, no rebirth, no return. Other physicists resist this permanence. They turn to quintessence, the idea that the storm is not fixed, but a field. Like the Higgs field that gives particles mass, quintessence would be a cosmic fluid, changing with time, waxing and waning as the universe evolves. If true, the fate of existence may not be sealed. The storm could weaken, slow the expansion, or even reverse it. In this vision, the storm is not eternal but dynamic, a force with history, capable of change. But then comes an even more violent possibility, phantom energy, where the storm grows stronger over time. Instead of fading, it intensifies, tearing galaxies, stars, planets, and eventually atoms themselves apart. This is the Big Rip, the most catastrophic fate of all. In such a universe, the frozen storm is not simply expansion but dismemberment. A storm that begins in silence and ends in annihilation. Another theory peers deeper into quantum foundations. According to quantum field theory, every particle has a field, and the vacuum is the lowest energy state of these fields. But calculations predict a vacuum energy 120 orders of magnitude larger than what we observe. The discrepancy is not small. It is the worst mismatch in all of physics. Known as the cosmological constant problem, it suggests that our understanding of the frozen storm is profoundly incomplete. Perhaps, some argue, the answer lies in string theory, where the universe is not made of point particles but vibrating strings. In this framework, the the storm arises from the geometry of hidden dimensions, curled tightly beyond perception. Each configuration of strings and dimensions would create a different vacuum, with different strengths of the storm. The multiverse emerges here, a vast landscape of possible vacua, each with different laws of physics. Our frozen storm is but one among countless others. If so, the question shifts, not why the storm exists, but why this storm? Why this balance, delicate enough to allow galaxies and life? Perhaps it is chance. Perhaps it is necessity. Perhaps it is selection. Only in vacua, where storms are balanced, do observers arise to ask the question. Other theories attempt to tame the storm by redefining reality itself. Loop quantum gravity suggests that space-time is not smooth but quantized, built of discrete loops. In this picture, the storm is not a field laid over space-time, but the texture of space-time itself. Reality would be grainy, woven from quantum threads, and the storm would be the vibration of that weave. The holographic principle extends the enigma further. Inspired by black hole physics, it suggests that all the information in a volume of space can be encoded on its boundary. If the universe itself is holographic, then the frozen storm may not reside inside space at all. Instead, it would be inscribed on the cosmic horizon, the edge of what we can see. The storm would not be within reality, but the script upon which reality is written, and yet speculation does not stop there. Some imagine that the storm is unstable, that we live not in a true vacuum, but a false vacuum, perched on a plateau of higher energy. If the field were ever to tunnel downward into a lower state, the storm would break. A bubble of new vacuum would erupt, racing outward at nearly the speed of light, obliterating all before it. This is not simply expansion, but replacement. The rewriting of physics itself. In this grim scenario, no warning would come. The frozen storm would end in an instant, without cause, without mercy. The constants that govern atoms, the forces that bind particles, would be reset to alien values. The universe we know would be erased, replaced by a reality where matter, chemistry, and life may not exist at all. Others offer a gentler vision. Perhaps the storm never ends, but transforms. In cyclic models, the universe expands, collapses, and is reborn, each cycle seeded by a storm of vacuum energy. What we see as silence may be only a phase, the quiet between breaths of an eternal cosmos. And beyond these scientific frontiers lies speculation so bold it borders on philosophy. Some suggest that the storm is not physical at all, but informational, that probability waves, quantum entanglement, and vacuum fluctuations are expressions of a deeper order, mathematics itself. In this vision, the storm is not the enemy of reality, but its essence. It is not frozen because it is waiting, but because it is eternal. The theories diverge, but they share a haunting unity. Each insists that the frozen storm is not optional. It is not an afterthought. It is the foundation upon which reality rests. Whether constant or changing, eternal or fragile, it defines what can exist, what can endure, and how the universe will end. And so speculation becomes reflection. The storm is not simply a physical puzzle, but a mirror. It forces humanity to confront its limits, the boundary between knowledge and imagination, between science and philosophy. The frozen storm at the heart of space is not just a question for cosmologists. It is the question of existence itself. The frozen storm at the heart of space cannot be touched, nor bottled, nor brought into the laboratory. It exists everywhere, filling the void, woven into the silence between stars. Yet humanity has never accepted mystery without pursuit. If the storm governs the cosmos, then science must find a way to measure its breadth, to capture its shadow, to chart its hidden movements. The quest begins underground, in the great caverns carved for particle accelerators. The Large Hadron Collider, LHC at CERN, smashes protons together at near light speed, peeling back layers of matter to reveal the fields beneath. In 2012, it confirmed the Higgs boson, the particle linked to the Higgs field, itself a kind of frozen storm, giving mass to particles. But physicists suspect that the Higgs may also be unstable, perched atop a false vacuum. If the Higgs field were to collapse, the frozen storm would unravel. Thus, each new collision is more than a search for particles. It is a probe into the foundations of existence, asking whether the universe is secure or temporary. Above ground, laboratories perform subtler experiments. Casimir effect studies place metal plates micrometers apart, measuring the faint pressure of quantum vacuum fluctuations. These delicate forces confirm that the void is alive, pushing and pulling without matter, whispering of unseen waves. Each refinement of these measurements is a test of the frozen storm itself, mapping its invisible contours. Yet Earth alone cannot reveal the storm. The cosmos must be studied on its grandest scales. Astronomers turn their gaze to the sky with vast telescopes. The Vera C. Rubin Observatory, rising in Chile, will track billions of galaxies, mapping how their light bends and stretches across time. Its mission, to trace the fingerprints of dark energy, the force accelerating the expansion of space. By studying how galaxies cluster and drift, Rubin's survey will illuminate the hidden hand of the storm, orbiting Earth. A new generation of space telescopes carries the search beyond the atmosphere. The Nancy Grace Roman Space Telescope, scheduled to launch in the 2020s, is designed to measure the acceleration of cosmic expansion with exquisite precision. It will study distant supernova, standard candles that reveal how quickly the universe swells. Each flicker of a dying star becomes a message from the storm itself. Even more ambitious is Euclid, launched by the European Space Agency. With its wide-field imaging, Euclid seeks to chart the geometry of space-time, unveiling how dark energy sculpts the cosmos. It looks not only at galaxies, but at the invisible scaffolding of dark matter, whose gravitational web interacts with the frozen storm in ways yet unknown. But perhaps the deepest insight lies not in the present cosmos, but in its birth. The cosmic microwave background, the faint afterglow of the Big Bang, carries subtle imprints of the storm's earliest stirrings. Future missions, like Light Biard and CMBs-4, will map the polarization of this ancient light, searching for evidence of inflation, a colossal surge of vacuum energy in the universe's first instant. If detected, it would confirm that the frozen storm once raged in unimaginable force, seeding galaxies from quantum ripples. Listening for echoes, physicists turn also to gravitational waves. Detected first by LIGO in 2015, these ripples in space-time reveal the most violent events of the cosmos. Yet beyond black hole collisions, they may carry signatures from the earliest universe, faint tremors from the frozen storm itself. Planned observatories such as LISA, a space-based interferometer, will extend this hearing into new frequencies, searching for whispers of the storm imprinted on space-time at birth. Meanwhile, analog experiments on Earth attempt to recreate the storm's phenomena in miniature. In ultra-cold laboratories, Physicists craft Bose-Einstein condensates and simulate horizons, imitating the behavior of black holes. Within these artificial voids, they detect faint radiation akin to Hawking's prediction. Though tiny, these tests reveal that even in the laboratory, the frozen storm can be coaxed into showing its edge. Supercomputers, too, have joined the hunt. Vast simulations model universes built on quantum fields, tracking how vacuum energy evolves across billions of years. Each simulation asks, is the storm constant, dynamic, or doomed to collapse? By comparing models with astronomical surveys, scientists inch closer to decoding the storm's nature. The search is relentless, yet it is marked by humility. The frozen storm is too subtle to grasp directly. It reveals itself only through consequences. The acceleration of galaxies, the flicker of ancient light, the faint pool of plates, the whisper of radiation at horizons. Science listens with instruments spread across scales from subatomic to cosmic, weaving data into fragile truths. Still, unanswered questions loom. Why is the storm so small compared to predictions? Why is it balanced so perfectly to allow stars, galaxies, and life? Is the storm eternal, or a fleeting pause before collapse? Each telescope, collider, and detector seeks not merely data, but an answer to these existential riddles. For in the frozen storm lies not only physics, but fate. If constant, the universe drifts into eternal expansion. If phantom, it ends in a catastrophic rip. If false, it may collapse without warning. And if dynamic, the storm may yet surprise us with futures unforeseen. The tools are sharpened. The listening has begun. Humanity stands on the shore of an invisible ocean, casting instruments like nets into the silence, hoping to capture the outlines of the storm that has no end. The storm lies in silence. It does not rage across skies, nor break upon mountains, nor scatter the oceans of the earth. Its theatre is larger than worlds, vaster than galaxies. It dwells in the very fabric of reality, the quiet tension stretched between nothing and everything, a storm without sound, a storm without end. For centuries, humanity believed the void was emptiness, an absence, a backdrop, a canvas upon which matter painted its dramas. But in truth, the void itself is the drama. The frozen storm is not a stage, but the play, not a silence, but a heartbeat. It has shaped the cosmos since its first moment, sculpting galaxies, seeding stars, binding light into patterns that stretch across eternity, and yet it remains invisible. It hides not behind distance, nor behind time, but in the nature of existence itself. The storm is the vacuum, the quantum fields, the restless balance between energy and silence. To contemplate it is to look into a paradox, a storm that moves without motion, that rages without sound, that builds universes while seeming empty. What does it mean for humanity to live in the eye of such a storm? The future of the storm is written in possibilities. If its balance holds steady, galaxies will continue their slow retreat until only silence remains. Stars will die, black holes will fade, and the frozen storm will stretch space-time into eternal night. This is heat death, a cosmos without contrast, where every flicker is extinguished, where even thought can no longer exist. If the storm is false, a metastable vacuum perched on the edge of collapse, then its quiet may shatter in an instant. A bubble of deeper nothing could form and expand at the speed of light, rewriting the rules of physics as it passes. No warning, no survival. The storm would not fade into eternity, but crash into silence in a single breath. If the storm is dynamic, alive in ways not yet known, then the future may hold transitions, eras when dark energy shifts, when the balance alters, when the storm's frozen surface breaks and reforms. Perhaps new physics will emerge, new structures, new kinds of existence born from its turbulence. And if the storm is eternal, unchanging, then perhaps it is not a prelude to silence at all, but the foundation of all universes, all realities. A storm that never begins, never ends, but sustains. The philosophers of old once asked, why is there something rather than nothing? The frozen storm transforms the question. For in truth, there may never have been nothing. The void is not absence, but presence, not silence, but a frozen roar too deep to hear. The cosmos is not built upon nothing, but upon this invisible storm, humming beneath the notes of creation. But if the void is alive, then what is existence itself? Are galaxies, stars, and lives merely eddies upon its surface? Are we patterns, formed from the fluctuations of the storm, temporary and fragile? If so, then what happens when the storm changes? The human heart recoils at such questions. It yearns for permanence, for solidity, for a cosmos indifferent yet stable, but science has revealed otherwise. Everything that feels firm, stone, mountain, planet, star, rests upon quantum waves, upon restless fields, upon an energy that is not constant, not final, not fully understood. The storm beneath all things is fragile, and so are we. And yet, fragility need not mean despair. To live in such a cosmos is to live within mystery itself. Our existence is brief, our knowledge incomplete, but our awareness, our capacity to even ask what the storm is, makes us participants in the deepest riddle of being. We do not stand apart from the frozen storm. We are part of it. Our atoms were forged in stars, shaped by its balance. Our thoughts flickered in patterns allowed by its quiet tension. Our lives are currents upon the storm's surface. To contemplate it is not to gaze from outside, but to feel the storm reflect upon itself. There is humility in this, but also wonder. If the storm is eternal, then so too are the questions it raises. If the storm is temporary, then our search becomes even more urgent, for knowledge itself is fleeting, destined to fade with galaxies into silence. Science has built telescopes to pierce the edges of time, colliders to probe the smallest structures of matter, detectors to hear the faintest whispers of space-time. All of them, in truth, are instruments not only of measurement, but of philosophy. For in searching the frozen storm, humanity is searching its own meaning. The silence between galaxies is not empty. It is charged, alive, trembling with possibilities unseen. We stand, as we always have, on its shore, listening. The data may come as faint pulses, as shadows on detectors, as distortions in the ancient light of the sky. But behind those numbers lies a question that science alone cannot resolve. What does it mean to live in a universe where the void itself is the most powerful force? Perhaps the frozen storm is a reminder that the universe is not secure, not fixed, not a monument, but a process. That being itself is contingent, uncertain, and therefore precious. That silence may hold more power than sound. In its stillness lies both terror and beauty. Terror, because it may end all things. Beauty, because from it emerged galaxies, stars, life, thought the fragile brilliance of existence. The storm will not end with our age. Long after the earth is gone, long after the galaxies drift apart, long after black holes dissolve into radiation, the frozen storm will continue, writing the last chapters of time. Whether it will collapse, endure, or transform into something unimaginable, no science can yet say. But perhaps that is the final gift of the storm. It denies us certainty, yet it gives us awe. It humbles, yet it elevates. It reminds us that to exist at all in the eye of a storm too vast to see is a miracle. The universe is not a quiet cathedral of silence. It is a sea frozen in tempest, holding its breath across eternity. To live within it is to ride its hidden currents, to ask questions it may never answer, to listen for a roar that may never sound. And when humanity gazes into the night sky, seeing only stars and galaxies, it must remember, what shines is not the whole. Beneath, around, within, the storm waits. A storm without motion, a storm without sound, a storm that is the heartbeat of existence itself, the frozen storm at the heart of space,